Hello, and welcome to Connecting Devices to AWS IoT Core, a part of the AWS Innovate online conference. My name is Simit Nambiar, and we are going to explore how you can connect your devices to AWS IoT. For many of you, this may be quite new, so we will share a short demonstration of a microcontroller running Amazon FreeRTOS connecting to AWS IoT at the end of this session. We hope that by the end of your time together, you will have developed an appreciation of the different ways in which you can connect your devices to the AWS IoT platform. So let's get started. If you knew the state of everything and could reason on top of that data, what problems would you solve? AWS IoT's mission is to help customers know the state of their devices and help them reason on top of that data so that customers can get deeper insights and solve their business problems. In this session, I will focus on how we help our customers to know the state of everything. The SDKs, libraries, frameworks, and even operating systems that we provide to seamlessly connect a wide array of devices to AWS IoT. Let us start by looking at the IoT device landscape. At one end of the spectrum, we have microcontroller or MCU-based devices. A microcontroller is a single chip containing a simple processor that can be found in many devices. MCUs frequently run operating systems which do not have built-in functionality to connect to local networks or the cloud, making IoT applications a real challenge. Amazon FreeRTOS helps solve this problem by providing both the core operating system as well as software libraries that make it easy to securely connect to the cloud, so that you can collect data from IoT devices and take action. Amazon FreeRTOS is based on the FreeRTOS kernel, a popular open source operating system for microcontrollers, and extends it with software libraries that make it easy to securely connect your small, low-power devices to AWS cloud services like AWS IoT Core, or to more powerful edge devices running AWS Greengrass. Microcontrollers are used widely in different industries and in a range of applications, including home appliances, sensors, fitness trackers, industrial automation, and automobiles. Amazon FreeRTOS provides everything you need to easily program connected microcontroller-based devices and collect data from them for IoT applications. You can get started by choosing a microcontroller that fully supports Amazon FreeRTOS features and capabilities from trusted providers like Espressif, Microchip, NXP Semiconductors, ST Microelectronics, Texas Instruments, or others from the Amazon FreeRTOS qualification program. Now, why is this important? We can say from our experience that porting applications to different microcontroller architectures is really hard and a time-consuming process. I still remember the time when I had spent a month in troubleshooting while moving an embedded application to a different architecture, only to realize that it was just a flag to the compiler that I had missed while cross-compiling. With Amazon FreeRTOS, customers do not have to spend months porting anymore and can now focus more on building great features into their products, leaving the heavy lifting to us. We have another class of devices that might not necessarily be running FreeRTOS, but would still need to connect seamlessly to the AWS IoT Core. The AWS IoT Device SDK helps you to easily and quickly connect your hardware device to AWS IoT. It provides enhanced features so that your hardware device can seamlessly and securely work with device gateway and device shadows. These SDKs include open source libraries, developer guides with samples, and porting guides so that you can build innovative IoT products or solutions on your choice of hardware platforms. The AWS IoT SDKs are available in various high-level programming languages like C, C++, Java, JavaScript, and Python. We also provide mobile SDKs for Android and iOS, which can be used to talk to the AWS IoT Core. Up next, we have those more powerful devices that act as smart home hubs or industrial gateways that require much more functionality than just connecting to the AWS IoT Core to send and receive messages. AWS Greengrass is software that lets you run local compute, messaging, data caching, sync, and machine learning inference capabilities for connected devices in a secure way. With Greengrass, connected devices can run AWS Lambda functions locally, keep device data in sync, and communicate with other devices securely, even when not connected to the internet. Using Lambda, Greengrass ensures your IoT devices can respond quickly to local events. Use Lambda functions running on Greengrass core to interact with local resources. Operate with intermittent connections, stay updated with over-the-air updates, and minimize the cost of transmitting IoT data to the cloud. Greengrass has support for different operating systems and CPU architectures. With Amazon Linux support, you could even run Greengrass codes on the AWS cloud. As I said before, Greengrass supports Lambda functions, and you can write these functions in Python, Node.js, and Java. Now that we have seen the device landscape, SDKs, and tools you can use, let us see how they connect to the AWS IoT core. On the left-hand side, we see the edge devices using the IoT Device SDK, Amazon FreeRDOS, and Greengrass to connect to the AWS IoT core. You can also see some of the devices connecting to AWS Greengrass without connecting directly to the cloud platform. We will now explore the different components that make up the AWS IoT core, like the message broker, the rules engine, and device shadows. AWS IoT Core is a managed cloud platform that lets connected devices easily and securely interact with cloud applications and other devices. The IoT Core allows you to easily connect devices to the cloud and to other devices. It supports HTTP, WebSockets, and MQTT, that is, the message queue telemetry transport, a lightweight communication protocol specifically designed to tolerate intermittent connections, minimize the code footprint on devices, and to reduce network bandwidth requirements. AWS IoT Core provides mutual authentication and encryption at all points of a connection so that data is never exchanged between devices and AWS IoT Core without a proven identity. It supports AWS method of authentication called SigV4, X.509 certificate-based authentication, customer-created token-based authentication using custom authorizers. Connections using HTTP can use any of these methods, while connections using MQTT use certificate-based authentication, and connections using WebSockets can use SigV4 or custom authorizers. With AWS IoT, you can use AWS IoT generated certificates, as well as those signed by your preferred certificate authority, or CA. You can map your choice of policies to each certificate so that you can authorize devices or applications to have access or change your mind and revoke access altogether without ever touching the device. You can create, deploy, and manage certificates and policies for the devices from the console or using the API. Those device certificates can be provisioned, activated, and associated with the relevant IoT policies that are configured using AWS IoT. This allows you to instantly revoke access for an individual device if you choose to do so. When you receive data from devices at scale, you would want it to be seamlessly routed to your applications or other AWS services. You can do this without writing a single line of code using the rules engine. The rules engine within the AWS IoT core can filter, transform, and act upon the device data on the fly based on business rules you define. You can update your rules to implement new device and application features at any time. AWS IoT Core makes it easy to route messages to AWS services like AWS Lambda, Amazon Kinesis, Amazon S3, Amazon DynamoDB, etc. Rules give your devices the ability to interact with AWS services. Rules are analyzed and actions are performed based on the MQTT topic stream. You can use rules to support tasks like writing data received from a device to an Amazon DynamoDB table, save a file to Amazon S3, send a push notification to all users using Amazon SNS, publish data to an Amazon SQS queue, invoke a Lambda function to execute your business logic, process messages from a large number of devices using Amazon Kinesis, send data to the Amazon Elasticsearch service, or capture a CloudWatch metric, send message data to an AWS IoT analytics channel. Before AWS IoT can perform these actions, you must grant it permission to access your AWS resources on your behalf. When the actions are performed, you incur the standard charges for AWS services you use. An AWS IoT rule consists of an SQL select statement, a topic filter, and a rule action. Devices sending information to AWS IoT by publishing messages to MQTT topics. The SQL select statement allows you to extract data from an incoming MQTT message. The topic filter of an AWS IoT rule specifies one or more MQTT topics. The rule is triggered when an MQTT message is received on a topic that matches the topic filter. Rule actions allow you to take the information extracted from an MQTT message and send it to another AWS service. Rule actions are defined for a wide set of AWS services. For example, by using a Lambda rule, you can call other AWS or third-party web services. With AWS IoT Core, you can create a persistent virtual version or device shadow of each device that includes the device's latest state, so that applications or other devices can read messages and interact with the device. The device shadow persists the last reported state and the desired future state of each device when the device is offline. You can retrieve the last reported state of the device or a set of desired future state through the API or using the rules engine. The device shadow makes it easier to build applications that interact with your devices by providing always available REST APIs. In addition, applications can set the desired future state of a device without accounting for the device's current state. AWS IoT Core will compare the difference between the desired and the last reported state and command the device to make up the difference. The AWS IoT Device SDK makes it easy for your device to synchronize its state with its device shadow by providing high-level APIs to interact with the device shadow. The device shadow lets you store the state of your devices for up to a year for free. The device shadow persists forever if you update them at least once per year. Otherwise, they expire. Now that we have seen the IoT device ecosystem and how various libraries and tools help to make it so simple to connect your devices to AWS IoT, let us dive a bit deeper to understand how it all works. There are three things that needs to be in place for a thing to successfully connect to send and receive messages to the IoT core. 1. Authentication. The thing would need to prove its identity. 2. Authorization. The thing would need to have the right permissions in place. Finally, you will use one of the SDKs, Amazon FreeRDOS or AWS Greengrass to connect to the IoT core. Each connected device must have a credential to access the message broker or the device shadow service. All traffic to and from AWS IoT must be encrypted over Transport Layer Security or TLS. Device credentials must be kept safe in order to send data securely to the message broker. AWS Cloud Security mechanisms protect data as it moves between AWS IoT and other devices or AWS services. Devices connect using your choice of identity over a secure connection according to the AWS IoT connection model. AWS IoT allows you to define custom authorizers that allow you to manage your own authentication and authorization strategy using a custom authentication service and a Lambda function. When using custom authentication, a custom authorizer is responsible for authenticating your devices and providing an AWS IoT or IAM policy to authorize actions in your account. When using AWS IoT authentication, the message broker authenticates and authorizes all actions in your account. The message broker is responsible for authenticating your devices, securely ingesting device data, and adhering to the access permission you place on devices using policies. Authentication in AWS IoT from a device's perspective is done mostly via TLS mutual authentication using X.509 certificates. AWS IoT Core provides device certificates which can be used by the devices to authenticate to the platform. Customers can also bring their own certificates and use device certificates via the just-in-time provisioning feature of AWS IoT. The next step is authorization. Once the thing or device has authenticated, it has essentially proved to the AWS IoT platform its identity. Now, a TLS secure transport has been established in the process. The next step would be to use MQTT to connect to the AWS IoT Core over the secure transport. But to actually connect via MQTT to the platform, the thing needs to have an IoT policy attached to its X.509 certificates, which will describe the various operations it can perform once authenticated. This is called authorization. Authorization essentially defines what a thing can do once it successfully connects to the AWS IoT platform. An AWS IoT policy is a JSON document that contains one or more policy statements. Each statement contains an effect, an action, and a resource. The effect specifies whether the action is allowed or denied. The action specifies the action the policy is allowing or denying. The resource specifies the resource or resources on which the action is allowed or denied. The policy in this example grants the vehicle permission to connect to the AWS IoT message broker using a particular client ID and restricts the device to publish on a specific MQTT topic vehicle/vehicle ID/position. They follow the same conventions as IAM policies. AWS IoT defines a set of policy actions that describe the operations and resources to which you can grant or deny access. For example, IoT Connect represents permission to connect to the AWS IoT message broker. IoT Subscribe represents permission to subscribe to an MQTT topic or topic filter. IoT GetThing Shadow represents permission to get a device's shadow. The last step is to use the SDKs and tools. As we now know how to authenticate using X.509 certificates and set up AWS IoT policies for authorization, we are now ready to connect the device to the AWS IoT Core securely and publish our first Hello World message using the MQTT protocol. Let us dive into the AWS IoT Device SDK to learn about the API that allows us to do that. We will be using the AWS IoT Device SDK for Python in this example. Let us create the thing, certificates, and AWS IoT policies using the AWS CLI or command line interface and link them all up together. The create thing command is used to create a thing record in the AWS IoT registry. We have created a bike with the name obike. The JSON document printed on the console just below the create thing command is essentially the response received from the platform. You can see that a unique thing ID has been created to uniquely identify this thing. Using the create keys and certificate API, we obtain the certificates required for authentication. This is the only time AWS IoT issues the private key for this certificate, so it is important to keep it in a secure location. We will now create an IoT policy for authorization. The policy document we will use to create the policy is called obike_policy.json. You can see that the policy is quite liberal and does not lock down the resources and action the device using this certificate can perform. However, we need to be careful in only providing access only to the required actions and resources in the IoT policy, as you will see later in the example. For now, this should be okay. The next step is to attach the policy to the principal. The final step is to attach the thing to the principal, although this step is not mandatory and has no effect on the authorization flow, but can help you keep track of what principal or certificate is attached to a particular thing. On the AWS console, you should now be able to see the following relations we have set up via the AWS CLI. That is, how a principal or certificate is linked to the thing and a policy. You can access this on the AWS IoT console by navigating to the Secure menu on the left-hand side and then clicking on the certificate ID, which was returned when we received the certificates. To summarize, what we have done till now, we have created a thing, a certificate, and an IoT policy using the AWS CLI. We've also linked everything together. The AWS IoT Device SDK makes the final step of connecting very simple by hiding the complexity of TLS and MQTT and wrapping it up in a few high-level API calls. In this example, we have changed the AWS IoT policy to lock it down to what the device can do. In this case, connect using a particular client ID and publish messages to a particular topic. In lines 3 to 7, we import the dependencies required for the program. In line number 10, we instantiate the AWS IoT MQTT client. Line 30, we set up the MQTT endpoint. Each AWS account will have a unique endpoint. You can find it on the AWS IoT console if you visit the settings page. This is your custom endpoint that allows you to connect to AWS IoT. Next, we configure the AWS IoT root certificate, which can be downloaded publicly. Private key and device certificates, which we received when we used the create keys and certificate AWS CLI command. We have now configured the client to connect to the AWS IoT platform, and once connected, can publish messages to the AWS IoT core. Line 15, we make the connect call. Once connected, we publish a hello world to a particular topic, which is the same topic we defined in the AWS IoT policy. To view the published messages and for testing purpose, AWS IoT provides a test console where you can both subscribe and publish to topics. By navigating to the test console, you can see the messages now being published by subscribing to the vehicle topic from the sample code as shown. During a POC or testing, it might be easier to physically copy the device certificates onto the devices. However, this might not be practical when devices are produced at scale. AWS IoT cores support just-in-time provisioning of device certificates, where manufacturers can register their own CA certificate on AWS IoT and create device certificates in the factories and flash them onto the devices. In this demo, I am going to demonstrate an ESP32 MCU running Amazon FreeRTOS to publish messages to the AWS IoT core. ESP32 is a series of low-cost, low-power system on a chip microcontrollers with integrated Wi-Fi. You can now take advantage of Amazon FreeRTOS features and benefits for microcontrollers using the development boards from Espressif. This enables you to easily and securely connect your ESP32-based devices to AWS cloud services like AWS IoT Core or to edge devices running AWS Greengrass. Let's jump straight into the demo. Let us first quickly compile the program and get an executable. I'm going to now flash the program onto the ESP32 connected to my laptop by using the make flash monitor command. This command does two things. It flashes the firmware onto the device and also starts monitoring the console output. We are now going to have a look at the browser to check whether we have any messages being received on the subscription. Well, you can see that the background color of the browser is changing every second. Let's also go to the AWS IoT test console to check whether we are receiving any messages by subscribing to the topic. You can see that there are messages arriving every second too. Now that the ESP32 device is subscribed to a control topic, I can control the onboard LED by sending a publish message with state on or off. Let us start by first turning it on. I'm going to send a state on message right now. The LED turns on. Now I'm going to turn it off by sending a state off message. And the LED goes off. We have now seen how a highly constrained microcontroller device can be connected to the AWS IoT core seamlessly with minimum effort. To gain more confidence and hands-on experience with AWS, access the digital training built by AWS experts. Attend our instructor-led classes by qualified AWS instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS, and validate your technical expertise with AWS and use practice exams to help you prepare for AWS certification. AWS also has a wide partner ecosystem to help you focus on your success and take full advantage of all the business benefits that AWS has to offer. To learn more about how APN partners can help you find the right APN partner for your needs, visit the AWS APN booth at our showcase. Finally, I would like to thank you for attending today and sticking it out until the very end of the presentation.